Okay, so hello everyone, welcome to lecture number 33. So last time we have started with half wave rectifier with resistive load, and we have seen how the circuit works, how the diode conducts only during one half of the half cycle. So during positive half cycle, diode is on and output is following the input. During negative half cycle, the diode is off and output is zero. So these were the input output waveforms. This is my input of the output of the secondary of the transformer. That is my input signal. And these are my output signal. As you can see, during the positive half cycle, output follows the input. During the negative half cycle, it's zero. All right. Now current nature is also same because it's a resistive load. So I out will be V out upon RL. And this waveform over here, VD1, is the voltage across the diode. As you can see carefully, when the diode is on, the voltage across the diode is zero, almost, we are assuming it. And when it is not on, the voltage across the diode will be same as your input voltage. And in this case, it is negative half cycle, so it will be negative. It will be following the negative half cycle. All right. And the maximum negative voltage a diode can withstand without damaging it is called as PIV rating of the diode. And here it is around minus Vm. All right. Now for the analysis part, we have to derive the expression for V out average, V out RMS, rectification efficiency, and ripple factor, and also transformer utilization factor. So let's start with V out average. So write down for the analysis part, V out average. So here we start with lecture number 33A. All right. So the first derivation, all these derivations will be valid provided we draw the input output waveform particularly. So we need to find the average value of the output waveform. So basically, let me just write it over there. Basically, we need to find expression for V out average. Now at the start of the AC circuits, right, we have seen that how to calculate the average value of a waveform. So now the waveform is like this. See, please see this. This is omega t. This is my V out. So for a half cycle, it's following the input, and for other half, it's zero. Again, it's following the input. Okay. This is pi, 2 pi, 3 pi. All right. This value is Vm. What is my period of this waveform? Pi or 2 pi? When does waveform repeat itself? 2 pi. So capital T period is 2 pi. Now we have to find the average value of this. We have done this before. So I hope that you all will be confident in solving this. All right. So what will be V out average now? Tell me the formula, or we can also call it as VDC. Its other name is VDC. So tell me, what will be the formula, general formula? 1 by T integral 0 to T V out D omega T. All right. And what is V out given by? V in, it was following the V in. And what is V in or VI, guys? Vm sine omega T. Okay. And that is happening between 0 to 2 pi. Now 0 to pi, output follows the input, right? So you can check this. V out is equal to Vi from 0 to pi, and from pi to 2 pi it's 0. Alright. So here it will be 1 upon 2 pi integral 0 to 2 pi V out d omega t. So basically 0 to pi will be V in, and pi to 2 pi will be 0. So we can write, please write along. This we have done it before. So 1 upon 2 pi integral 0 to pi Vm sine omega t d omega t. Alright. Because from pi to 2 pi it's 0. V out is 0. Now let us solve this further. So you can write still, you can write it down. Pi to 2 pi, it's 0 d omega t. Okay. So let's find the next value. What is integral of sine omega t? Minus cos? Yeah. So you can take Vm upon 2 pi common. Integral of sine will be minus cos omega t, where omega t is going from 0 to pi. Alright. What is, here you can take it as minus Vm upon 2 pi. What is cos pi? Anyone? Cos pi minus 1. So this will be minus 1 and this will be 1. So what do you get over there? Minus 2. So minus minus gets cancelled, and finally you get V out average as Vm by 2 pi into 2, which is nothing but how much? So V out average is Vm by pi. Okay. Now in the exam, if they ask you, find the average value of a half wave rectifier, you need to derive this. Okay. So this is my average value of my half wave rectifier, output rectifier. So we can write it as VDC is equal to, what is 1 upon pi? 0.318 times Vm. Now what does it represent in terms of waveform? In terms of waveform, what does it mean? So if I draw this, okay, for half cycle it is of, alright, this is omega t, this is V out, and this is Vm. What does it mean? V out average is this much. What does it mean? See, this value is how much? Vm. Okay. What's the average value of this waveform is positive, right? So average value of this waveform is this. And what is this value? VDC or Vm by pi. So basically, this is my DC value. And where is my AC value? This is AC and that is DC. Got it? So my DC value or the average value of this waveform is, how much is that? Vm by pi times. So how much is that? I mean VDC is how much actually? 31.8% of Vm. So my average value of the waveform is 38.1% of Vm, or peak value, maximum value. Got this? So what is the output? See, if you can see over here, AC and DC both are present. Okay. So output of half-wave rectifier, what we want at the output of rectifier, a DC. We don't get a DC, we get a pulsating DC. What do you mean by pulsating is DC? AC waveform which contains a DC waveform is pulsating DC. So this waveform has both AC and DC components. Okay, that is proven from the average value. Is this understood? Yeah. Okay. Sometimes in the exam, instead of asking you voltage, they can ask you current, average value of current. How will you find I out average? Or you can call it as IDC. Anyone? It's a resistive load, so it will be V out average upon RL. Or we can call it VDC upon RL. And how much is that? VDC is Vm upon pi RL. So that's the value. Now, over here, if you look carefully, Vm upon RL, Vm upon RL is called as Im. So this can be written as I out average Im upon pi, where Im is Vm upon RL. Okay. So that's the output current average value. Now, next we have to find out the RMS value of the output. So next write down B part. Actually second, right? Okay, A, B. So we need to find V out RMS. What is V out RMS? RMS value of the AC component of output. So write down, it's the RMS value of AC component of output. So how do you find this? There is a standard formula. V out RMS is 1 by T integral 0 to T V out square omega T d omega T. Now here you can write the whole raised to half, or you can write this V out square RMS is 1 by T 0 to T V out square d omega T d omega T. V out of omega T d omega T. Okay. So let's find this out. So here we have T is equal to 2 pi. And from 0 to pi, V out is V. So what is Vi? Okay. So let's find it out. V out square RMS is 1 upon 2 pi. I'm directly writing 0 to pi. Is it okay? You're understanding? From 0 to pi, V out is Vi. And from pi to 2 pi, it's 0. So let me write it fully first. Okay. Now we can write it formally as 1 upon 2 pi integral 0 to pi. What is this? Vm square sine square omega t d omega t. How do we solve this further? We take Vm square upon 2 pi common. And what is sine square? We can write it as 1 minus cos 2 omega by 2 into d omega t. Okay. Now we'll open a bracket. Uh, this will be Vm square upon 2 pi. What is integral of this? We can treat it as, it's 1 minus, okay? This is wrong. By 2 here, na? Or it is over here. Where is 2? So 1 minus cos 2 omega t divided by 2, or it is 1 minus cos 2 omega t divided by 2. Here. 2 is coming entire, 1 minus cos, or it is 1 minus entire, right? So what will be the first one? Omega t by 2 minus sine 2 omega t by 4, right? And here omega t is going from 0 to pi. So V out square RMS will be Vm square upon 2 pi. Tell me what this value is. This will be pi by 2 minus 0 minus sine 2 pi by 4 minus sine 0 by 4. Tell me what is sine pi, sine 2 pi? 0. Sine 0, 0. So what do you get over here? Tell me. V out square RMS will be Vm square upon 2 pi into pi by 2. Okay. So which will be Vm square by 4. But this is V out square RMS. So what will be V out RMS? Vm by 2. And that's the answer. Please note it down. If V out RMS is Vm by 2, what will be I out RMS? Im by 2. Where Im is Vm upon Rn. Okay? RMS value is 50% of maximum value, that is Vm. Vm by 2. Did you get this? Written the formulas. These expressions can be asked in exam as a part of your analysis for half wave rectifier. They can ask you derive the average value and RMS value for a half wave rectifier. So you need to derive these two expressions. Completed? Yes, any doubts over here? Plain simple mathematics is there and you have done enough practice for RMS and this thing, average value. Now the third part is we need to find rectification efficiency. So listen carefully. What do you mean by rectification efficiency or rectifier efficiency? It is denoted by the Greek letter eta. So percentage eta will be PDC upon DC power upon AC power into 100. So how do you define rectification efficiency? Write down. It is the ratio of DC power at the output to the applied input AC power. Okay? It is the ratio of DC power available at the output to the applied input AC power. Now, tell me what is PDC formula? Power is V into I. This DC power. So it should be basically VDC into IDC. What is VDC? Average voltage. IDC is average current. So multiply to 2. You get DC power. And how much is that? What is VDC? What is IDC? We can call it as. We can have the formulas for this. Correct now? V into I, V square by R or I square R. Then tell me AC power. This is challenging. AC power is how much? See, average value represents the DC quantity. RMS content represents the AC quantity. So it will be, yes, V out RMS into I out RMS. Or simply we can call it as VRMS, IRMS. Okay? This has also three forms. V square RMS by RL or I square RMS into RL. Why we have three formulas in DC? We have three formulas in DC because load is resistive load. Okay. Now let's finally calculate PDC. Everyone please concentrate. This we are doing for first time. Let's take this formula. VDC square upon RL. Do you know what is VDC? We have just now calculated. Vm by pi square divided by RL. So tell me how much is this? Vm square upon pi square RL. Let's call this equation number A. Now PAC output input AC applied will be VRMS square upon RL. What is VRMS? Just now we have found out, right? How much is that? Vm by 2, not root 2. So it will be Vm square upon 4 RL. That's B. Okay. Now, let's calculate the efficiency. So PDC upon PAC into 100 we have to do. So how much is that? Vm square upon pi square RL divided by Vm square upon 4RL. So tell me which all quantities gets cancelled? First of all Vm square, then RL gets cancelled. What is left out? Into 100. What is left out? Tell me. 4 by pi square into 100. Calculate how much is that? How much it is? Is it 40 point something? 40.5? 3. Anyone with a calculated value? 400, huh? 56, yeah. So this is the rectification efficiency or rectified efficiency of a half wave rectifier. So please note it down. This is for half wave rectifier. Okay? Yes. So for all three rectifiers, this is the procedure. We have to find V out average, V out RMS, rectification efficiency, and now the ripple factor. Next is this one you have completed. Okay. So let's go to the next part, D part, ripple factor R. You remember when you did mobile battery charger experiment, after the capacitor, you were getting a AC output which was looking like this, right? Correct? So this is called as a ripple voltage. And ripple factor will determine the amount of AC content in this ripple. Okay, let's find it out. First of all, let's define what is this ripple factor R. So write down the derivation, write down the definition. It is the ratio of, please write it down. It is the ratio of, I'll appreciate if you'll keep quiet. If you do not writing, please keep quiet. It is the ratio of RMS value of output component, output AC component to the DC component of rectifier output. Okay. The smaller the value of the AC component, the more effective is the rectifier. Is the ratio of RMS value of the output AC component to the DC component of the rectifier. Just as I showed you now, in the output you have a AC component and DC component as well. So the ratio of the RMS value of the both will give you the ripple factor. So technically speaking, the R will be IAC upon IDC. Or we can calculate VAC upon VDC. Now, how do we calculate AC component? IAC will be, now this derivation is not there for you. Just write it down. It is I out RMS square minus IDC square. AC component will be given by square root of RMS value square minus the average value square. So if I divide this by IDC, what do we get? I out RMS can be written as IRMS square divided by IDC minus 1. We can rewrite this, right? If we take IDC inside, it will take IDC square, right? So this is what is ripple factor is. So R will be square root of IRMS square upon IDC square minus 1. So this is will be a ripple factor. Okay. Now, for a half wave rectifier, this is the general formula. For half wave rectifier, what is IRMS? Im by 2. What is IDC? Im by pi. So let's substitute this ripple factor over there. So square root of Im square by 4 divided by Im square by pi square minus 1. So here you will get it as pi square by 4 minus 1. Calculate how much it is. It will come out to be 1.21. Please check this answer. And this is for half wave rectifier. Okay. Square root of pi square by 4 minus 1. Is it 1.21? So it's very high. The half wave rectifier is pretty bad because the ripple content is more than 1.21. That is 121%. It should be less than 1. Okay. So in the same line, we have completed now a half wave rectifier. So we have started with the circuit diagram, the working input output waveforms, expression for V out average, expression for V out RMS, rectification efficiency, ripple factor. There is one more transformer utilization factor that will cover for all three together. Okay. So now we start with full wave bridge rectifier. So we complete this 33.8 and now we start with full wave. So write down the topic as not a full wave bridge, full wave center tap rectifier. Full wave bridge will cover next lecture. So write down the heading full wave, not bridge, center tap rectifier. Now y'all tell me what was the problem in half wave rectifier? One half was getting, the output was getting 0. So both the halves were not utilized properly. So in a full wave center tap rectifier, I'll show you conceptually what is happening. So conceptually, let's say this is my black box, which is your full wave center tap rectifier. So here we have input as AC, of course, output of the secondary. This positive, this is negative. So output of full wave rectifier will be like this. Are you understanding? Both the cycles will get utilized. Okay. For negative half cycle also you will get an output. For positive half cycle also you will get an output. So output is more closer to your DC. Alright. So let's start. Understood the concept? You'll get, that's why it's called as a full wave. Full AC waveform is getting utilized. That is the concept. Now let's start with the circuit diagram. Everyone please pay attention. So here again you have to draw the transformer. So first of all draw the we have studied center tap transformer in your labs, mobile battery charger experiment. So how does what is it containing? These are my primary windings. This is my laminated core, iron core. And at the secondary, what do we have? We have a tapping over here at the center, and that is going to the ground. Understood? That is called as center tapping. What is this? This is my, let me highlight it further. This is my AC mains. What do you mean by AC means 230 volt, 50 hertz, single phase supply. This transformer is called as anyone? Center tap transformer. Center tap step down transformer, right? Why step down transformer? Number of primary turns are more than number of secondary turns. And why it is called as a center tap? Because at the secondary, at the center of the winding, there is a tapping which is going to the ground. So this number of winding and this winding are same. Let's say this is 20, so this will be 10. Let's say the secondary windings are 10, so 5 over here, 5 over here. What does it mean? It means the following. So this is my primary of the coil. This is my primary winding of the coil. And these are my two secondaries. So over here, what voltage we get is as follows. Listen over here. So let's say this point is A, this point is B, and this point we let's say call it O. So if I have at the secondary at the primary, if I have this voltage over here like this, okay, let's say the ratio is 10 is to 1. Let's say 230 is getting converted into 23. So how much voltage will be available between 0 and 8? Tell me, anyone? If the total voltage over here is VI, VI by 2 will be available over here and VI by 2 will be available over here. Meaning, if 230 to 23 is the rating, if this is 23, 11.5 will be available over here between O and A and 11.5 between O and B. But what's the difference? At O and A, you get the waveform like this. And at O and B, you get the waveforms out of phase. That's the difference. So at the end, if you take at together at between A and B, it will be like both the waveforms 0 to 23. Are you understanding? That's why this transformer we write it as, let's say, 12 0 12. Okay, so let's say this is 12, this is 0, this is 12. Are you understanding? So between O and B you get out of phase signal, between O and A you get in phase signal. This is the meaning of center tap transformer. You will have two voltages available at the secondary, one is positive, one is negative. If you want to, what is the voltage between A and B? Got it? Addition of 2. So this will be, let's say, 12 volt. This will be 12 volt. This will be, let's say, 24 volt, according to this. Are you understanding? Try to understand. So note it down, please. Achha, what is VI called as? Secondary voltage of transformer. The entire working of center tap transformer, center tap rectifier is based on this principle of center tapping. Okay? Understood this concept? So I'll keep this as it is for your understanding. What I will do is I'll draw another diagram. So just we revise, we have a secondary primary winding, and then we have this laminated iron core. Then at the secondary side we have center tapping. So what do we do now is, since this is my AC mains, this is my AC mains. Okay, so what do we do here is, we connect a diode over here, one, we call it diode number 1, and here we connected diode number 2. Now remember, for all the rectifier circuits, we have to consider resistive load. So here, we connect them together, and then we connect it to resistive load. This is my Vout. So this is RL. Now, one crucial thing is, please remember this ground, this yellow color ground, this ground, and this ground are same. 1, 2, 3, they are same. So some books show you that are connected between this and this. So that will create confusion. Instead, I've drawn it separately. Are you understanding what I'm saying? Some books will show you are connected over here. That is also true. Because this ground, and this ground are same. What about the primary winding ground? Well, that is different. This ground is different. Huh? This ground is isolated from this ground. That's why transformer does not only transforms the AC voltage, it also isolates the primary from the secondary. Okay, all right. This time, how does the circuit work? You know how does the diode work? When it is forward bias, it will behave as a short circuit. When it is reverse bias, it will behave as an open circuit. Now, tell me what will happen. So, first of all, this type of this is called as what? What is this called as? Center tap, step down, transformer. Okay. What is this voltage over here? As I've told you earlier, this voltage is VI by 2, and this voltage is VI by 2. So if VI by 2 is, let's say, 505, what is the meaning? This is VI by 2, 0, VI by 2. That's the meaning of it. Okay. Now, what happens during positive half cycle? Tell me. So during positive half cycle, let me mark over here as this is point A, this is we can call it point B. So during positive half cycle of the AC input, what is the A at? Positive, right? This is positive, right? Here it is positive, here it is negative. So tell me which diode will be on. When the input is positive half cycle, you know positive half cycle, right? Input over here is positive half cycle over here like this. My point number A is positive and point number B is at negative. So which diode is on? So during positive half cycle, tell me which diode is on. Positive half cycle, this is positive, na? So that D1 is on, and here we have negative. So D2 will become reverse bias. So only D1 conducts. Okay. So we can write over here for positive half cycle, D1 is forward bias, therefore it is on. D2 is reverse bias, therefore it is off. All right. So how does the circuit become now? Let me draw it quickly. So this diode will be replaced by what? On, right? And this will be open, right? At below, I have connected to, it will be open or closed? Just wait. D2 is off, so it will be replaced by open circuit. And D2 is on, it will be replaced by a short circuit. So this is open circuit, this is D1 and this is D2. Now this is connected to, this is plus minus V out. Now tell me, how does the current flow in the circuit? Let me highlight this part. This is during the positive half cycle. So A is positive, B is negative. This is AC mains. Tell me, how does the current flow in the circuit? Like this. This is positive, this is ground, right? How does the current flow? Let me take this. It's flowing like this. See, it starts with point A. Listen here. It starts with point A, go to D1, then go to RL. This is RL, and then go to back to ground, and then again back to your A. So it's an entire loop. Okay. So this is the flow of current. So remember, flow of current is from positive to negative of the voltage, output voltage. So here we have output voltage also. Now tell me, what is output voltage here? Same as VI or VI by 2? Output voltage will be VI or VI by 2? It will be VI by 2 now. Because it's flowing from here to here. Okay? Understood the working? So because the diode D1 is on, your I out also flows. and iot will be V out upon RL. Alright? So this is what happens during positive half cycle. Now, tell me what happens during negative half cycle. During negative half cycle, what happens? Remember, during negative half cycle, B point is positive, A is negative. Negative half cycle, no? So negative half cycle, it's reverse, polarity is reverse. And now, B is positive with respect to A. To which diode is on over here? As you can see, D2 is on and D1 is off. Are you understanding? D2 is forward bias, D1 is reverse bias. So let's draw the circuit again over here quickly, everyone. So this is off, D1 is on, D2 is on. And here we have B out, RL. And here it is center tapping. This is A, this is B. So how does the current flow? This is 0. D2 on. How does the current flow? From B to D2 to RL to ground. Again to back to. So current flow from B, D2, RL, again back to B. So again, here, listen carefully, everyone, very important thing. The flow of current will be from positive to negative, right? Even if the input is negative, my output will be positive. You didn't get it? See, first case mein I out was flowing from positive to negative. Yes or no? In second case also I out is flowing from positive to negative. That means if current is positive, V out also will be positive. So here output will be again following Vi by 2. But this time it will be plus Vi by 2. That means if I have this input over here like this, if this is my secondary output, sorry, how will be my output of the full wave rectifier? Can you tell me? So in first case, diode D1 is on. In second case, diode D2 is on. But again, the output is positive. Why positive? As you can see, the current flows from positive to negative over here, even when D2 is on. And in the first case also, current was flowing from positive to negative. So if the current is positive, your voltage will be positive because voltage is I out into RL. So in both the cases, your I out is positive. So therefore, this is called as full wave rectified output. So this is my full wave rectified output. This is my Vi. Actually, Vi by 2. Okay, full wave rectified output. All right. And what is this voltage given by? This peak value is Vn. Understood? First positive half cycle D1 is on, negative half cycle D2 is on, but it will maintain the current in the same direction. That's why for both the cases output is positive. Now write down this equation. V out is equal to Vi by 2, that is Vm sin omega t if omega t is going from 0 to pi, and it is again Vi by 2, that is Vm sin omega t if omega t is going from pi to 2 pi. This equation will help you to calculate the analytical values. Alright, let's call this equation number 1. Okay, now circuit diagram is over, explanation is over. Now what is left? Input output waveforms. Understanding this? Full wave center tap rectifier. So write down, draw now next input output waveforms. Okay. Everyone, please draw the input waveform first. Okay, let me close the PDF and open again. Yeah. So first is my input, which is Vi by 2. Input waveform will be sinusoidal. Acha, tell me, where is this waveform available? At the output of secondary of the transformer. Okay. This is not AC mains, huh? So this will be Vm. This will be minus Vm. This is pi to pi 3 pi. Next end is down over here. Next I'm plotting V out. So how will be V out now? Positive half cycle D1 is on, output will follow the input. Negative half cycle D2 is on, output will follow the positive of input. Okay? Yeah? And next cycle, it will repeat itself. So here it is, D1 is on, D2 is on, D1 is on. And the cycle continues. This voltage over here is Vm. This is Vm and this is Vout. This is the output waveform for a full wave center tap rectifier. Now, next I will draw the current waveform. Will the current waveform be of the same wave nature as current waveform will be same nature as output voltage? Yes or no? Yes, because it's a resistive load. What will be the difference? What will be the difference in current waveforms? The difference is in the amplitude. Here it will be V out upon RL. Here it will be IM. So this is I out waveform. And what is IM given by? So these are my current waveforms. And if you can see carefully, my average value of my output is always positive. Even before calculating, my average value is positive. What about my average current value? Again, it is positive. Now, the most challenging voltage across the diode D1 and D2. If I am able to draw that successfully, they have understood everything. The voltage across the diode D1 and D2 when they are on and off. Now tell me, when the diode D1 is on, देखो ध्यान से देखो, when the diode D1 is on, what is the voltage across the diode D1? 0. Okay, but when the diode D1 is on, what about the diode D2? What about the voltage over here? This is negative, no positive. So reverse Vi is connected over there. मतलब across the diode D2 there is a negative voltage appearing, not positive. Negative voltage appearing. Now in the second case, when the diode D2 is on, the voltage across the diode D2 is 0. But across the diode D1 is, here this time this is negative, right? Second half cycle this is negative positive. Now, so negative voltage is appearing across the diode D1. That means whichever diode is off, negative voltage is appearing across that diode. Okay? So if I draw the waveforms over here of D1 and D2, first let me draw the waveforms of D1, VD1. Okay? Help me out to draw this. This is voltage across D1. So for the first half cycle it is on or off? On. Correct? And other half, negative half cycle, it will follow the input, which is negative. And again off, and again it will follow the input. Okay? So this is where it will be. This is VD1 and this is minus VM. Now, if you can draw VD2 also similarly, What will be the picture over here? This is VD2. VD2 is off in the positive half cycle. So it will be correct. Here it will be 0, and here again it will be like this. And this is minus Vm. So if I see the PIV rating of the entire circuit, what it will be? It is Vm or 2 Vm? Both the tags collectively together. 2 Vm. Why? Yes. For the entire half cycle, it will be 2 Vm. Got it? So these are my input output waveforms for a full wave center tap rectifier. Alright? So I'm giving you some work. For this rectifier, full wave center tap rectifier, derive the expression for V out average, V out RMS, and come tomorrow. Okay? Then I'll show you the expression for rectification efficiency. Acha, what do you mean by 40 point? How much did you get? Rectification efficiency of earlier one? 40 point something, right? 40.5 something. What is the meaning of that? That means a rectifier is able to rectify only 40.6, remaining 59% is wasted. Efficiency means that. Efficiency means that, right? So half wave rectifier is only 40.56% efficient. We'll see here the efficiency should be double. Why? Because both the half cycles are utilized. So that also we'll see tomorrow. So for tomorrow, derive the expression for V out average and V out RMS and come.